Welcome to The Explainer. Today, we're cracking open the Chemist's Toolkit. We're going to learn the secret language that literally describes, well, everything.
I mean, it sounds like something out of a sci-fi movie, right? But this is exactly what chemistry is all about. And the craziest part? It all comes down to just a few simple building blocks and, a handful of really clever tools. So let's do it. Let's start putting that toolkit together piece by piece, starting with the absolute basics. Okay, first up, we got to know what everything is actually made of. Like, what are the tiny, tiny particles that make up, the chair you're sitting on or the air you're breathing? Okay, so everything, and I mean everything, is built from three key players. You've got the atom, that's kind of like the basic Lego brick. Then, when these atoms link up, they form a molecule. Think about the oxygen we breathe, O2. That's two oxygen atoms hanging out together. And finally, if an atom gets an electric charge, either positive or negative, we call it an ion. That's it. Atoms, molecules, ions. Those are our core building blocks.
Okay, so we have our building blocks. Now we need a language, right? A way to write them down. We need a kind of universal alphabet so chemists everywhere can understand each other. And, this language didn't just appear out of nowhere. It took centuries. The ancient Greeks gave us the word atomos, which means indivisible. But that was just an idea. It wasn't until 1808 that John Dalton really gave us the first set of rules with his atomic theory. And then, just a little while later, this chemist, Johannes Jacob Berzelius, comes along with a simple but totally genius idea for the symbols we still use today.
And his system was it's so elegant. For a lot of elements, it's just the first letter, right? C for carbon, O for oxygen. Easy. But what about when letters repeat? Well, some get two letters. And for the really old elements, the ones known since antiquity, he did something super clever. He used their Latin names. That's why gold isn't G, it's Au from the Latin aurum, and iron is Fe for ferrum. It's a system that works no matter what language you speak. It's truly universal.
Okay, so we've got our particles, we've got our alphabet, but now we hit a major roadblock. How do you weigh something you literally can't see? I mean, seriously, how do you weigh one single atom?
Well, the short answer is you don't. Just look at this number. It has 23 zeros after the decimal point. It's completely useless for doing any actual calculations. It's just too small. So scientists knew they had to find a workaround, some kind of clever hack to deal with these ridiculous numbers. And the solution they came up with was just brilliant. They basically said, you know what? Forget the actual weight. Why don't we just compare everything to each other? So they created a relative scale. They picked one atom to be the standard, the benchmark. So now an element's relative atomic mass isn't its weight in grams at all. It's just a number, a score, that tells you how heavy it is compared to that standard. And this is the atom they picked to be the king, carbon-12. They just decided, okay, this atom right here, its value is exactly 12, period. And now every other atom is just measured against it. So if another atom is twice as heavy, its score is 24. If it's half as heavy, its score is 6. It's that simple. So elegant. And it completely solved the problem. All right, next tool in the kit. This is a biggie. So, we can weigh atoms relative to each other now. Great. But chemical reactions don't happen with one or two atoms. They happen with billions and trillions and, well, even bigger numbers of them. So how in the world do you count that many? The answer is a concept called the mole. And look, I know the name sounds a little weird, but don't let it throw you. A mole is just a word that means a number. It's exactly like how a dozen means 12. You have a dozen donuts, you have 12 donuts. A chemist has a mole of atoms. They just have a specific, and yes, very, very large number of atoms. And this is that number. It's called Avogadro's number. Just look at it. It's 602,000 billion. It's a standardized amount, and it's basically the perfect bridge that lets chemists go from thinking about single, invisible atoms to working with amounts they can actually see and weigh in a lab. Okay, and this is where the magic happens. This is where it all clicks together beautifully. Remember that relative atomic mass, that score we gave each atom? Well, get this. That number is also the exact mass in grams of 1 mole of that element. It's incredible. So carbon, with its relative mass of 12, well, 1 mole of carbon atoms weighs exactly 12 grams. Oxygen has a relative mass of 16, so 1 mole of it weighs 16 grams. See? It perfectly connects our made-up relative scale with the real-world scale in the lab. It's just genius.
So let's take stock. We've got our particles, we've got the symbols to write them, we have a system to weigh them, and a way to count them. Our toolkit is complete. We can finally start writing the actual recipes for chemistry, what scientists call chemical equations.
But before we do, there is one absolutely unbreakable rule we have to follow. And it's this: the law of conservation of mass. It basically says you can't create or destroy matter. In a chemical reaction, atoms don't just vanish or appear out of thin air. They're just shuffled around, rearranged into new combinations. This is the fundamental rule of the game. And because of that law, every single equation has to be balanced. It's like a puzzle. You just have to make sure you have the same number of each type of atom on the left side as you do on the right side. So you start with your unbalanced recipe. Then you go element by element. Okay, let's balance the hydrogens first. You add a number here, a number there, but wait, that messes up the nitrogens. Okay, so now we balance those. And then you do the oxygens. It's a bit of a back and forth, but in the end, you do a final check and bam! Everything's equal on both sides, the law is satisfied.
And once it's balanced, that equation is so much more than just some letters and numbers. It's the whole recipe. It tells you what you start with, what you end up with, and the exact proportions you need of everything. It's where all the tools we've collected, the symbols, the masses, the mole, all come together to give us this perfect, powerful blueprint for how matter changes. Which brings us to one last big question. Our entire toolkit is built on this one rule, that matter can't be created or destroyed. But what if it can't? What happens in those reactions where the law is broken, where atoms aren't just rearranged, but are literally smashed apart or fused together? Well, that's when you step out of the world of chemistry and into the wild world of nuclear physics. But you know what? That's a story for another explainer.